This is exam 1 for Physics 102, Spring 21. These are the free response questions. Remember, I'm looking for your work on these, so I want to see all of your work on them for full credit. So number 1, sketch the E-field vectors at the point A. So the first thing we want to do, let's get the right color here. At point A, I have an electric field due to this charge. I imagine a positive test charge, and the positive test charge will experience a force in that direction. So this is going to be my electric field E2. And then what does the electric field do to the other one? Well, this is a positive charge, so my E1 will be down and in that direction. So that's part A. Also, I want to see the coordinate system and the angles, and I'll probably actually change this so that it includes that. And this angle then, recognizing that this is a triangle, this angle theta is the inverse tan of opposite over adjacent. That's 4 over 3, but this is a 3, 4, 5 triangle. A 3, 4, 5 triangle will always have this angle be 37 degrees. That's the angle opposite the small side, and the angle opposite the big side will be 53 degrees. That's 90 minus 37. So this opens up, so this angle will be, let's see, this is going to be 53 degrees. So 53 degrees, that's my angle. So that's part A. And then show your work for calculating the x and y components of that vector. So I'm going to draw my vectors again down here. E1 is just right here. E1, I calculate my magnitudes of E1 up here. That's going to be 9 times 10 to the 9th times Q, which is 32 times 10 to the minus 9 coulombs, divided by the distance squared. This is 4 meters from here to here. It's the same as right here. So that's 4 squared. That's 16. That gives me there. This cancels. So that gives me 18 newtons per coulomb. And then E2 is going to be 9 times 10 to the 9th, 25 times 10 to the minus 9, divided by the distance. That's 5 meters right here. It's a 3, 4, 5 triangle. Cancels there, there, and there. That should be at a 9. That's 9 newtons per coulomb. So coming down here, E1 is 18 newtons per coulomb. And then E2 is 9 newtons per coulomb at an angle of, what did I say it was, 53 degrees. Remember, this angle right here opens up onto the big side of the triangle right here. So it's the bigger of the two angles, 53 degrees. Or you can do this inverse tan of opposite over adjacent. Now, find my x and y components. See, this was E2. E2x is going to be 9 cosine of 53. E2y will equal to 9 sine of 53. That's 5.4. And that's 7.2. So those are my x and y components of that vector. If I redraw that, I'll have 7.2 right here, 5.4 right here, and 18 down here. Okay? So show your work for calculating x and y components of the electric field vectors. Boom, did that. Show your work to find the magnitude of the electric field at point A. So for part C, what I need to do is, actually, no, I'm sorry, I missed a step. So I also have to do this where I find the resultant of these. So my coordinates keep changing colors, don't they? What I do is I only have one vector on the x direction, that's the 5.4. And in the y direction, I have 7.2 minus 18. as well, 10.8 or 11 newtons per coulomb. It's negative, so that's why it's down. Notice I did this was positive, this one was negative, so I get a negative 11, and that's why my vector is pointing down. So those are the x and y components. Now my resultant vector is going to be down in that third quadrant. To find the magnitude of the electric field, I say the square root of 5.4 squared plus 11 squared. And I get 12 newtons per coulomb. So that's part C. And then for part D, I need to find the angle. I want to first find this angle. I'm going to call it phi. That angle phi is the inverse tan of the opposite over adjacent. That's 5, not 5.4, 11. That's the y component divided by 5.4. I get 64 degrees. But recognize that I wanted it measured from the plus x-axis. So I have to add 180 to it because this angle is 180 degrees plus this angle, which was 64. 180 plus 64 is equal to 244 degrees from the plus x. And that jives because I know my third quadrant goes between 180 and 270. So at least that angle is right in that it's in the third quadrant as I've drawn it. Look, it'll be very helpful to you if you draw these pictures along the way. It helps me to grade just to see that you know what you're doing, but it'll also help you to track along what you're doing. So just to recap, these are the answers. 5.4 and 11, where the x and y components of the resultant vector. That's for B. And then A was just sketching the vectors and showing the angle for those vectors. Okay. You place a 3 coulomb charge at point A. What force does the charge experience? Okay, well now I know my electric field. I know that my electric field is 12 newtons per coulomb. So if I want to know my charge, or my force rather, that's pretty straightforward. It's just F equals QE. Remember, this comes about from our definition of electric field, which is a force per unit charge. Here, I'm just looking for the magnitude, so I'll just take the magnitudes of both of those. So this is going to be 3 coulombs times the electric field, which is 12 newtons per coulomb. Notice my units cancel there and give me 36 newtons. So that's right. And then what is the potential at point A? Well, to find the potential, I'm going to do the sum of all the individual potentials. So at point A, it's going to be K times Q1. Oh, I just realized that I'll make this Q1. I'll fix that on the exam. So it's going to be the sum of the potentials. That will be V1 plus V2. So I'll make this Q1. So that'll contribute our V1. That's going to be K. Well, I'll just go ahead and put in K. It's 9 times 10 to the 9th times Q, which is 25 times 10 to the minus 9. Now I'm going to put a negative right here. Remember, potential is a scalar quantity, so I'll include those negatives. It doesn't mean that they have a negative direction. It has to do with, are they giving or taking away energy? Kind of like what we had last semester when we were dealing with work. We can have positive and negative work. Work is a scalar quantity. Divided by R. R is 5 meters. Plus V2, which is going to be 9 times 10 to the 9th times 32 times 10 to the minus 9 divided by the distance, which is 4 meters. And this is positive. All right, so fortunately, a lot of these numbers cancel out. Let's go through. That goes away with that. This goes away with that and leaves me 5. This goes away with that. This goes with that. That gives me 8. And I'm left with, 9 times 5, that's 45, negative 45, excuse me, plus 9 times 8 is 72. And 72 minus 45, that's 22, 27 volts. So that's the answer. That's the potential at point A. A proton moves from a potential of 8 volts to a place where the potential is 2 volts. What is the speed of the proton? Sorry, I have to pause for just a second. Okay, so I have this proton that's moving across a potential difference. I want to remind you that potential difference is energy per charge. In fact, if you look on your equation sheet, where is it? Right here. Sorry for that. So right here, I have the potential is energy per charge. Now, remember, there are some sign things that come in that have a negative here, a negative there, but fortunately, since I'm just asking for the speed, it doesn't really matter about the signs. I'm not really asking for anything about directions. But what is important is what is my change in potential. That's going to be V final minus V initial. That's going to be -2 minus 8, which is a -10 volts. But again, I'm looking for the speed, so that negative doesn't really mean anything to me. That's my change in potential. And then also I can say that the energy, the kinetic energy, is equal to my change in potential times, not G, times Q. That's got this from here. I got this from this equation right here. Even though it says potential energy there, we can generalize it for just any kind of energy, for our kinetic energy. We did that in class. So that's going to be equal to, then, if kinetic energy is equal to that, it's going to be equal to 1/2 mv squared, where v is the speed. I'm looking for the v then. Let's go ahead and solve that for v. That's going to be 2 delta v q over m, and then I take the square root of that. So that's going to be the square root of 2 times 10 times q. Q for a proton is 1.6 times 10 to the minus 19. That's right, isn't it? That's the fundamental unit of charge, divided by the mass. And that's on the equation sheet, but the mass of a proton is 1.67 times 10 to the minus 9, 10 to the minus 27. It's right here. Okay, and then there's our fundamental unit of charge. Make sure you're aware of what's on that equation sheet for your exam. So I have 1.67 times 10 to the minus 19 kilograms. All right, so I get 4.4. Yeah, that makes about right. Makes sense. 4.4 meters per second. Let's see. This. Oh no, shoot! I made a mistake here. That's not right. This should be 27. Let me pause for just a second. Okay, when I do that, I get 44,000 meters per second. All right, this last one, I want you to sketch 5 to 6 electric field lines for this configuration. Use solid lines for the E field, and then sketch 4 to 5 equipotential lines for this configuration. So I want to see both field lines and equipotential lines. Field lines will start at a positive charge and go into a negative charge, like this. I'll have another one go right there. But then because I have an excess of charge in the -4 coulomb, that was the wrong way, I will have an excess of field lines here. And since I have 3 coming out right here, I have to have 6 going in. I'm going to draw another one like this. That would be, oh, shoot, I did it wrong again. All right, not having a good afternoon. So that's what it should look like, something like that. What I'll be looking for is that whatever number of lines you have here, you have twice that number of lines here, and then also lines come out of this charge and go into this charge. Those are the field lines, and then for the equipotential lines, I'll be looking for those equipotential lines to be at an angle of 90 degrees with the field lines. So here, they'll look like this. Here they're going to be a little bit different. They're going to come around like this and then go like that. Something like that. All right, you can go through. Something like that. Notice how they sort of curve around those charges. Yeah, so that's it. Now let's go into the multiple choice part of the test. Consider this configuration of charges. Which vector best represents the force vector acting on the lower +2q charge? Now let's say the +2q charge is a distance d, in a distance 2d from these two charges as shown in this figure. So if I draw these are the same charges, but one is twice as far away. And because it's twice as far away, that means that the force on that will be 1/4 of the other force. So F is kqq over r squared, right? That's Coulomb's law. If I double r, that means I quarter the force. Let me show you what that looks like. So if I draw a force right here, that's the repulsive force between these two charges right here. Then these two charges are going to attract one another, but notice that it's twice as far away, so it's going to have a force that's 1/4 of the first force that I drew. Now because of that, if the two forces were equal, the answer would have been C. But because they're not equal, the answer is going to be D, that this big vector over here is going to pull that resultant vector over towards it. So D is the right answer. Consider these two charges where X is at a point equidistant from either charge. Where can you place a charge, either positive or negative, along the dashed line where the net force on that charge is 0 newtons? So where can I put a charge? Can I put it over here? If I put a charge over here, let's just say it's positive, it'll feel a big attractive force towards this charge, and then a smaller repulsive force, quite a bit smaller, from that charge, so not there. If I put it here in the middle, it feels an attractive force towards this and a repulsive force from this. I can't get a net force of 0 in the middle, in between those two. Well, what over here? So if I go over here, I feel repelled from the +3. I should get a big repulsive force, and then due to the -3, I get a small attractive force. So not going to get 0 over here. Not going to be there, nor there, or there. Not in between the charges, so none. E is the right answer. The force between two charges, which are now separated by 2 meters, is 32 newtons. If the force is now 2 meters, what is the separation of the charges? So I have F is equal to kqq over r squared. I start out with the force being 32 newtons, but then it decreases to 2 newtons. That means that I have a factor of 16 by which it decreases. It goes from 32 to 2. I divided by 16 to get to 2 newtons. In order to get that factor of 16, I have to have a factor of 4 right here because it's squared. So the distance now has increased by a factor of 4. That is, it's gone from 2 meters to 8 meters. Consider this configuration of charges. If Q1 has a magnitude of 2 coulombs, and I know in fact that it's plus 2 coulombs, what is the sign and magnitude of Q3? Look, a trick with these, just count the field lines. So I have 1, 2 field lines. So it's like each field line is attributed to 1 coulomb of charge, because I have 2 coulombs, 2 field lines, 2 divided by 2 is 1. So over here I count the field, 1, 2, 3, 4, 5, 6. That means that I'm going to have 6 coulombs over here. This is positive 2 coulombs. Look, my field lines are coming out, so that's going to be positive 6 as well. By the way, can you tell what Q2 is? 1, 2, 3, 4 coulombs, and it's negative. So that would be Q2 would be -4. Consider the previous configuration of charges. Where does the electric field have the largest magnitude? So to find the magnitude of my charges, I want to ask where are the field lines the closest? Now, A, the field lines look pretty far apart. D, there's no field lines out here. And so it's either C or B. And it's hard to tell how close those are. I mean, I've drawn the field lines at B closer. They really are closer there, but it's sort of hard to tell. However, I can also go and say, well, this is a 4 coulomb charge and this was a 6 coulomb charge. So if I'm closer to the 6, if I have a bigger charge, it will create a bigger electric field. So B is the right answer. Should have been able to tell that from the figure, but you can also discern it from just the difference in the charges. What is the magnitude and direction of the force on Q2? Let's just calculate it. So this is going to be F23. And this is going to be F21. F21 is the force on Q2 due to Q1. F21 is 9 times 10 to the 9th. 1 times 10 to the -4. 4 times 10 to the -5. Divided by 2 squared. I can get some cancellations here. Boom, boom, boom. That's just 9 newtons. And then F23, 9 times 10 to the 9th. 4 times 10 to the -5, 4 times 10 to the -4. Notice I'm not putting the signs on these. I've already considered the signs when I was drawing the vectors, and the 4 times 10 to the minus 5 comes from here, 4 times 10 to the minus 4 comes from there, and then my distance is 4 meters, and that's squared. So 4, 4, and 4, that cancels out. This cancels with that, and that leaves me with 9 newtons. So I have 9 newtons to the left, 9 newtons to the right. That gives me a net force of 0. Two charges are configured as in this figure. Where is the E field equal to 0? Okay, so uh, this is a good problem. I really like this problem. You should be able to discern the answer without actually doing any math. If you start trying to look at the math, it gets a little hairy. And I'll give you more space on this. Let me write that down. So number 7, I'll give you more space. Two charges are configured. Let's just start looking. To the left of the plus 2 nanocoulomb charge, so it's 4 meters. But let's just think about to the left of it. If I have my positive test charge right here, I feel a repulsive force from this plus 2 coulomb and a repulsive force from the plus 8. So that can't be right. And let's look at these. What about over on this side to the right over here? I have a repulsive force from this one and a repulsive force from this one. Or, yeah, so that means the E fields are both in that direction. So those can't be right. Now I have 2 more. I want to get away from the big charge. So I'm going to have to say that my answer is going to be somewhere over here. Now I have 2 answers. B is right here, and C is right here. So if I were to pick between those, I would have to pick B. Now let me show you how you would calculate that. Let's call this Q1 and Q2. I'm not saying that you should do this. I think this is the harder way to do this, but I call that Q1. Q1, the electric field due to Q1 is going to be there, E1, and the electric field due to Q2 is going to be E2. Now to find out where is the electric field 0, I would say E1 is equal to E2. Right, because I want them to be equal and opposite to one another. I know all along, from here all the way over to here, all along that dotted line, the electric fields are going to be opposite, but I also want them to be equal. So that's going to be K times 2 nanocoulombs divided by, let's call this X, divided by X squared. That has to equal to K times 8 nanocoulombs divided by, I want to know what this distance is, and whatever that is, it's going to be 6 minus x squared. My k's cancel, my nanos cancel, not my 2, that doesn't cancel, although I can cancel that 2 and solve for 8. Now, I can solve this for x. It's not terribly easy to solve. I have to deal with this quadratic thing down here. You can solve it for x. I think that y'all are capable. But since I already have these options, I can just plug in 2, and let's see if 2 works. I have 2 divided by 2 meters squared equals to 8 divided by 6 minus 2 squared. So that's 2 over 4 equals 8 over 4 squared, or 16. Those are equivalent to one another, so check. Again, I don't recommend you do it that way. I think that you can work through this conceptually and get to the right answer without any issue. I hope that most of you did that. But this is how you would do it. That's probably a little bit higher level for a little bit higher level class. Objects typically become electrically charged by doing what? Acquiring electrons from another object. It's hard to lose protons. You actually become a different element when you lose protons. Electrons just don't divide into pieces. That's not really a thing. And neutrons don't decay into a proton-electron. Well, that's not how objects typically become charged. All right, you bring a negatively charged rod near to a neutral conductor but do not touch. What is the charge distribution on the conductor? If I'm not touching, I'm going to get an induced charge. That means my positive charges will be here, my negative charges here. Physically what's happening is those electrons on this neutral conductor are rushing towards the end. So I have a positive and a negative. That's going to be A. Magnitude of a charged electron is A. Which of these vector property of charge? Not a vector. It's a scalar, it's quantized, and it's conserved. That's there. What must be done to a capacitor and increase the hold it can charge? Charge it can hold. C is kappa epsilon naught A over D. So I can increase the area. I can decrease the separation. I can add a dielectric. Let's see. So not that. 2 works. 3 works. 4 does not work. It's either 2 or 3, so A is the right answer. I have this capacitor consists of these two metal plates. I want to calculate the capacitance. That's going to be 4. Area is 0.2. Even though there are two plates, I just use that area. Let's see. I can cancel that with that and give me 2. That goes away and gives me this, gives me -6. So I get 0.4 times 8.85 times 10 to the -6. I really recommend that you do that. I get 3.5 times 10 to the -6 farads. That you do that, write out your numbers when you're taking standardized tests or my tests. That way you're not putting everything in your calculator. You're just prone to make more mistakes when you're using your calculator. Parallel plate capacitor connected to a battery has that charge. If the plates are moved twice as far apart, what is the new value of the charge? So it's connected to a battery. That means that the potential is constant. And I know that Q is equal to CV. I also know that C is epsilon naught A over D. If I'm moving them far apart, that means I'm halving my capacitance. If I'm halving my capacitance, I'm halving my charge. So I'm going from 20 coulombs to 10 coulombs. What is the primary purpose of a capacitor? To store electrical energy. So there's map. If an electron is at point B, where will it move to? Well, you remember when we talked about the mountain, and we said that a proton will move downhill, but an electron will move uphill. It will move from low to high potential. So if an electron is right here, that's like a potential well. It's not going to move from that point, because in order to move to that point, it would have to move from high to low. So it's going to remain at point B. By the way, if I put a proton over here, that would be a potential well for the proton, because it's going to move from high to low. And to move out of there, it would have to move from low to high. So these are potential wells. This is sort of like a topographical map, by the way, this potential map, where each line represents an equal potential line. If the distance between points B and D is 6 microns at the far right, what is the electric field at this point? Remember we had this unit for potential, volts over meters, for electric field that had that unit. So the electric field is equal to a potential difference divided by my delta X. That's on your equation sheet. Oops. On your equation sheet, where is it? Oh, it's right here, that relationship between V, E, and X. So I'm looking for the electric field. That's going to be delta V. Between B and D, that's going to be 24 volt potential difference. Right, because I'm moving from 10 to -14. That's 24 volts. Divided by delta X, which is 6 times 10 to the -6. That cancels, leaving me 4. So 4 times 10 to the 6 newtons per coulomb. Where's the potential 0? So I'm looking for places where the charges are equidistant to one another. That doesn't work. C3, see, that doesn't work. C, that doesn't work. D, so -1. See, none of those really work. I just picked random pairs of charges, so E is the right answer. If the distance between two negative point charges increased by a factor of 3, what is the potential energy? Well, potential energy is KQQ over R. If I increase this by a factor of 3, this becomes 1/3 of its original value. An electric field is a measure of force per unit charge. All right.